Right.
We'll
Also,
go from there.
also, may I just say,
hello, other calculus peeps.
There you go.
hello. May I just say it is so much easier to learn calculus than physics through your lectures because the way you do your lectures with the writing on it, I can actually see everything you're doing.
I am
versus
so glad. Okay,
if Ms.
good.
Bear wants to go to the board and do something.
Yeah,
Yes,
Mrs. Bear she has troubles with Zoom. I mean, and she has this way where she can set up like a camera so we can see what she's writing. And I think that works pretty well. I actually do prefer the in-person. I guess like I'm sure everybody prefers in-person too.
Totally.
I don't know.
Yeah,
I just think
totally
your way of going about it is easier to watch in the lecture version.
Yeah, thank you, Christopher, so much. I do appreciate that a lot. Just so I know, because
you have 149 subscribers on YouTube.
It's from his college.
A lot of people.
It's from his college.
Taking your class.
Maybe YouTube will notice. They'll start paying me soon. Just kidding. No, I do it for the college level as well.
Yeah. Monetize your calculus videos.
There you go.
Turn off my ad blocker. Turn off my ad blocker to support my calculus teacher.
Okay, guys, real quick here, just so we see it. So chapter 3, this is in front of you guys here. So I'm really interested in just making sure you guys can take derivatives of functions. That's it. That's the main goal here. So It started off, well, first of all, 3.2 started off just by using the derivative. Can you take definition based upon the derivative? Can you sketch the graph? And that was 3.2 as well. Just sketch the graph sketch the derivative. Let's see, use the f of x to sketch the derivative. So I kind of understand you're looking at slope. That's kind of what I'm seeing in 3.2. 3.3, 3.5, 3.6, 7, 8, and 9, and 10. Literally, can you give me derivatives? So this test will be about that. On top of that, it'll be 3.8, which is the equation line tangent problem.
All right.
So if you can do that, that's great. The one thing I probably should mention is 3.10 or 310. Just like implicit differentiation, just like the chain rule, there is a logarithmic way of doing differentiation, right? So kind of be mindful that there's a function that you do logs, you take derivative of log functions, right? That's one piece, right? But then the log differentiation is actually a method that you would use in order to take derivatives of stuff that doesn't even have logs inside it. Okay, does that make sense? There's a kind of twofold piece there.
I think so.
Okay, no, we'll cover it too. We'll totally cover it as well because that's
I'm a bit confused. So is that like 3.10? That's an additional thing you did?
Oh no, it's part of the chapter itself.
Okay.
So the chapter 3.10 it goes into exponential functions. So e to the x. You guys remember e to the x from sometime along algebra 2?
I do remember that.
So we take rid of those, and then we take anything that has a base and a variable in the exponent, right? So any power function. And so let's get that as we go through this. I think it would be just helpful. Make sure we get there. Let me just make some blank slides here, and then we'll get started here. Okay, but I just want to make sure you guys are comfortable with the study guide.
Yep.
Okay.
Just have to catch up on a couple lessons.
Yeah, I understand like the study guide, like what it's asking.
Okay.
Yeah.
Then the
final
study guide's going to be
concepts. I might be a little like on.
Definitely still need to study some more.
Okay, and so let's do this here because this is today. I don't mind doing another session this Wednesday, and then you guys will have that Thursday to take the test. We're good Thursday or Friday.
All right.
Okay.
Will that help?
That sounds great. Yeah.
That sounds great. Yeah.
I know being outside the classroom is way different than being inside the classroom.
Yeah.
Okay, just don't tell the calc students I gave you an extra day. Okay.
Depressing.
Too late, you're recording.
Oh, shucks.
Oh no. Cut
Wait,
that part out.
edit the
I
files.
could cut that out.
Cut that part out.
Okay, so let's go through as much as we can. Just going through this. I'm going to have to stop my video. And then I can still see you guys.
Cool.
And I'm going to grab my
Still
pen.
see our beautiful faces.
Mm-hmm. Let's see if I can put it on. Oh, yeah, that's so cool. Okay, so I can put it on PowerPoint and then still see you guys. Okay, because it pops in front. Okay, talk to me. Let's do that later. Let's start from chapter 3 onward here. You just throw out homework questions you guys are stuck on, and then we'll do it again.
I don't remember the exact homework question, but I think it would be nice to go over using the graph of a function to sketch the derivative.
Mm-hmm.
That was, I don't think I quite understood how to do it when I did the homework way back then, and looking back at it, I'm not totally clear on how to do it now too. So
Okay, perfect. Let's go with, I'm going to just grab some homework questions from there. So it's not necessarily homework questions that you guys have, but we'll cover those as well. We're good? Just to get us started though, on 664 off of 3.2. Are we good there if you guys can get there?
64 of 3.2. Let me pull that up on my homework because I actually did that one.
Oh, awesome.
Right? No, wait. 64 is
it's
not
60
something we did too.
65 is on there.
Yeah, never mind. I did
yeah, 65 is on there.
65.
Let's get started with 64, then we'll jump to 65. Just want to get you practice.
Scrolling 65. Ah, yes, graphing.
Mm-hmm.
Woohoo!
And so what we want to really understand here is when we look at this stuff, we're trying to plot the slope values. And if we understand that, we should be all good to go. So on the bottom right here, here's going to be my graph of my, one, two. Here's my derivative graph on the bottom corner.
Mm-hmm.
And so what we normally look first is we look for minimum values and maximum values when the tangent line is 0 or when the slope is 0. So I notice like right here, that guy has a tangent line of 0 or a slope. Sorry, I should say slope of the tangent line would be 0. And what tangent line means is it just hits at a one specific point. That's it, right? No 2 points like we did in algebra, right? Tangent line. Slope of the tangent line means you're hitting that graph one itsy bitsy point. So at that point, it looks like 1/2 over here. So on my graph over here, I'm going to make a point right here at 0. All right, then I'm looking for any other ones. And it looks like a little bit after 2, isn't there? There's a.
So why do you put it at in between 1 and 0 again?
Oh, sure, because on the graph itself, when the graph comes down,
Mm-hmm.
notice it's coming down, it's coming down, it's coming down, and right at about 1/2, that's when it straightens out and then it starts curving upward.
Ah, okay.
And so that this slope right here was negative all the way through, right? Because there's a negative slope.
Yep.
The graph is going down, down, down. And so you have a slope that's negative, 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 and turns the corner, starts becoming positive. But our derivative graph, the points there are what the slope is on the original one.
Okay.
So it looks like a little bit after 2, just right there, just tiny bit after. I don't think it's right at 2, a little bit after 2.
It's like 2.3, 2.2.
Yeah, somewhere. I'm going to put another dot like that because I know the slope there is 0 again. And so kind of have to get this in your head, and it either clicks or just takes a while here. So I have a very negative curve here, and it starts curving nicely to a flattened curve. So I go from a very negative slope, negative slope, all the way down to finally a 0 slope. Are we good?
Mm-hmm.
So then what happens here is it's the dots. Something, okay, I have a negative. Here's my dots now. A negative, negative slope. And it gets to a 0 slope. So the slopes of one graph are the points in the other.
Oh, wait, let me write that down.
Okay.
The
All right.
slopes
Of f of x.
graph.
Okay, that makes a lot of sense. All right.
Okay, so then in between the 1/2 and a little bit above 2, now the question is, what's the slope there? Positive, negative?
That's a kind of a sort of positive slope.
Yeah, it starts off from a 0, right? But then it becomes positive, positive. Notice it's interesting too. It becomes a positive and it's curving up. As it curves up like this, it becomes a steeper positive slope, right?
Yep.
And then it starts doing this. And we'll get into that in chapter 4. That's called concavity. But like right about here, then it starts actually becoming less steep, less steep, less steep, and eventually hits the 0 marker. And so what we have here is we have dots now again. It becomes positive, right? The slope here positive is becoming even higher positive, and then about halfway there or so, it's now becoming less steep. So now it's coming down like this because it's less and less positive now.
Mm.
And we'll do some other ones here in just a bit here, just to make sure we got it. Okay, then after that 2.2, whatever it was, what's happening there? What's happening with the slope?
Then it starts getting negative.
Yeah, and then it starts getting more and more negative, right? Each time we pass 3, it's really becoming negative. So then at that point, it just starts going downhill from there. And then we just stop. So there's my slope of my derivative. And it's not going to be exactly perfect. This is just a start of it here. Once we actually start taking derivatives, it's called analytical graphing eventually. But when we take the first derivative, second derivative, then we'll actually put it together perfectly. This is just to realize slopes of one graph are points in the other. Okay, let's start 65 then. So 3.265. I have this graph. Okay, so it looks like it comes down. I'm going to do it like this here. And so in between 12 and 8, it sort of flattens out right there. 1, 2, 3,
10.
Right there. And then it goes down. And then what do you say? Right at 3, doesn't it? It seems like it's right at 3. And then it just shoots up. Whoa, not that bad. It just starts shooting up. Okay, let's do this again. Let's see where we get to. One, 2. And notice the x coordinates, they're going to be more standardized, right? Because when it's happening is the same time when the slope is happening, right? All right, you guys talk to me. Where are my zeros?
Well, kind of at maybe at 1/2 or 1.5 or 1.3.
Ah, okay. Hold on. Let me go back.
Well, I think
0
that's
at the
over. I think it's over. I think it's past 1.5. I think it's like 1.7 or something.
Okay. So I'm
Or
going to say
probably more like 1.6.
I'm going to say your guys looking at it wrong. So where's my where are my 0 tangent line slopes?
Oh, that kind of 0. Oh, okay. There's one at in between 12 and 8. No, that's my bad.
12 and 8, probably around 10 because it's half.
Yeah.
No, still no.
But
The zeros are at occurring at. I don't care about the y value, right? I care about when it's occurring.
Oh, right. That's zero
So
for zero
it's
for
0.
x.
Mhm.
So it's 0. Okay. And then there's one kind of in between 2 and 3.
Yeah, I'm looking at the book itself. I'm going to call it 3 because it's
All
like
right.
right there. So there's my
Is it?
zeros. That's at least to me right there. Boom. And it has this
Alright.
little sharp curve. If you want to put it a little bit before 3, that's fine. I'll give you credit on the test for that even, Christopher. Just not at like -12. Call it almost 3.
Fair enough.
Okay, so we got that. And so now let's talk about the slope, or think about the slope here. So notice as it comes down, looks like it starts off, it's in between -1, -2, I guess. That's when we have the slope coming down.
Mhm.
Very negative, is that right? Very negative.
Very negative.
Uh-huh. And then it hits a 0 here. And
Mhm.
then it starts becoming negative again. And then it gets really negative again, and then it comes off again back to 0. So I guess we're going to plot that. So I have negative, 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 negative to 0, right? And then again, negative, 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 again to 0. So if I were to plot this, let's see. There's my little dots. See if you guys agree here. I'm going to go this way. I'm going to get to, and you want to make them smooth curves. So there should be no jots, because if it's a smooth curve, it's going to be a smooth curve on the derivative. So notice we come up to 0, and it's a smooth curve. We're curving it out.
Mm-hmm.
But then afterwards, the slope is still negative. So then what we're going to do is we're going to just change it up and still keep on going negative. So that means it hit a maximum point at 0, and then it starts going down again.
That is confusing.
Because the last one on 64, notice it went from a negative to a positive, right?
Yeah.
So if we went from, let's contrast this here. So if it goes negative to positive, these little graph lines, these little lines right here, these little dots, they just kind of break through the 0.
Okay.
On this one, because it goes from slope of negative, hits the 0 back to negative, we do a little bit of a curve there. Curve it back. Okay, and eventually right at 3, or a little bit before 3, it's going to hit 0 again. So we're going to nicely curve it back. And this time, after 3, you could tell it's going to go positive, and it goes positive quickly. Right.
So would we make that like a sharper?
Yeah, you can even make it like a sharper. And then when we do analytical graphing, that's when we're actually going to put numbers together. We're going to find exactly what that value is, and we'll go for it. But this is just getting this whole idea. I'm
Okay.
more curious in the shape of your graph and making sure you can find zeros, and making sure you're either above the x-axis or below the x-axis when you're doing that.
Okay.
And so here's my curve. Okay, boom.
Okay.
All right, one little sneaky thing I should tell you. You ready?
Mm-hmm.
You guys talk to me here from algebra. Do you guys know what kind of curve this is when it goes like this?
Is that
Tangent. Oh well, that's
a
no.
cubic?
A cubic, you got it. That's a cubic curve. It's actually a negation of a cubic curve, right? So
yeah, wouldn't a cubic curve be if it was positive?
Yeah, so it would go like this. It would go through here and goes like that, right?
Yeah.
Mm-hmm. So yeah, it's a cube, at least a power function of a cube. And notice what happens with the derivative. That looks like a negation of a
X squared.
Square function, right?
Yeah.
And notice when we've been doing derivatives, if we take derivative of negative x cubed, it's going to become a negative 3x squared, right? So
Yeah, that
the
makes
powers always
sense.
go down by 1.
All right.
So on 65, this guy, notice that there's almost like 2 bumps here.
Mm-hmm.
And so if there's 2 bumps, it's kind of that little process. It's x to the 4th because the 2 bumps. when you take derivative of it, it's going to be somewhere in the neighborhood of a power function of x cubed. We're good as the powers go down each time we take a derivative.
Okay.
That's cool.
All right. What do you guys say? Need a 66 or we can jump to 67? What would you like?
I mean, I think I understand it now.
Yeah.
So I think I'm actually good for that part of 3.2.
Okay, perfect. Christopher, you good?
Yeah,
As
I'm
well?
good.
Okay. All right, on to next ones here.
Let me look at my notes.
I don't have a whole lot of questions.
I think during some of the like 3.6 videos and later, I was a bit confused on how you guys were getting the derivatives that quickly. But I think after doing some of the homework, I started to kind of get into the flow of it. But just to kind of
Sure, yeah.
review.
3.6 particularly, or?
I mean, I think that's kind of, I don't know, that's just when I remember.
Yeah, sure, absolutely.
Being a little confused.
So let me thumb through it here. So first things first, that's the introduction to the chain rule. And so all right, the chain rule. So what is that all about? Is the fact that if you have functions that are stuck inside other functions, and so something like this, what we find we should do is, let me back up just a little bit here. So this function right here, x squared, right? If this was the function, and let me just kind of name a whole bunch of functions here. The derivative would be just 2x, right? You take the power rule, right? You stick the guy in front, and then you take 1 from the exponent. Well, our function now is, I'll just call it g to the x, is 3x plus 1 to the square root. So it's still a square function, right? Except now there's more stuff inside it. And so what the chain rule says this, it says you go from the outside in. It's like peeling an onion. You take the top layer, you do whatever you need to do to that one, and you keep on going down. So take the derivative of this guy would be still the power function in play. Still the 2 goes out in front, and we subtract 1 from the exponent, leaving you a 1. And then what we do is we multiply it by the derivative of the inside. So peel away the onion. You got to the second layer now. So it's 3x plus 1. Derivative of 3x plus 1 is just 3. And you're done, except we do have to simplify it here. So 3 and the 2 can be multiplied together now. So now this is 6. And then depending how your book wants to see it, it could either leave it like that, or it can multiply it all the way in and leave it like that.
Interesting.
So
that's cool.
Yeah, that's the chain rule. That's a way to.
Okay.
So that's how you started doing it faster and faster. Okay.
Yeah, and calculus is exactly that. We went from definition. Remember that when we did that first time? And once you create these extra little rules, we just start using them. It just goes faster and faster. This is, guys, I want to tell you, this is 300 years of math history packed into about 2 years of math. We good? So you guys are learning a lot. And I'm proud of you guys for doing that. That's really cool.
And you said this was like a semester of calculus in college?
It is, yep.
Right.
And so in college, there are 3 different levels of calculus. Usually it's calculus labeled as calculus 1, calculus 2, calculus 3. And what we do here is we introduce the derivative, which you guys have been introduced to already. And in fact, we actually know we do all the work of derivatives here. That's calculus 1. And then you're introduced to itsy bitsy part of integration, which we'll do April-ish or so, maybe March. Okay, but integration is huge. We use that for a lot of stuff. And so we take a whole semester 2 to talk more about integration, integration by substitution, the chain rule for integration, all that stuff. And eventually you come out with, I hate to scare you guys, about 81 formulas of substitutions and integration formulas.
81?
Wow.
Uh-huh.
What fun.
That's going to be a big cheat sheet.
And if the professor is kind to you, he'll just photocopy the first, how the front cover of the textbook, because they'll have those formulas on there. Like, okay, use the front cover.
Okay, big front cover.
And then third semester calc is 3D. So vector spaces, vector fields, all that stuff.
That sounds fun.
So by the time you're done, you've done 300 years of really mathematics, the development of mathematics from 1500s to 1800s.
Okay.
All right. Fourth class would be sometimes they do this as just a application to engineering.
When does it go into 4D?
No, that's it. It stops at 4. So that's just if you go into engineering, you do that, and if you don't, I didn't because I went to theoretical mathematics. So it was like, okay, nah, applications, who cares?
That does actually, it got brought up in physics. We started talking about topology, which, and I was wondering if, like, you knew about any, like, sort of calculus thing that was related to that. Because I'm fairly certain that it's related to calculus.
Oh yeah, absolutely. So first of all, what we do, getting off topic here, totally awesome. We try to press 3-dimensional space onto 2-dimensional space.
Yep.
That's the first thing we do. And so what we do is we do vector fields. And so how something flows, and you kind of think of air pressure, right? And then let's say this one goes like this. Right. And so the longer the arrow, the higher the magnitude, because these are vectors, right? And so we press that onto 2-dimensional space. And if you could do that, then you can do calculations at that point, right? Things we can't do that, then we do go into, it's mentioned in the book, but if we start modeling, let me just do just a quick, this is Earth, or any kind of spherical object that's rounded. Literally.
Damn, you're really good at drawing circles just quickhand.
Yeah.
Oh my gosh.
Lots of practice. Okay. So that would be the tangent line, correct? On a curve.
Yeah.
And you kind of think about a 3-dimensional space. And we have something called the normal line. And the normal line is, is a line that's perpendicular to the tangent line that's going to go through here. So there's your that's a normal, and there's I think 2 homework questions right at the end of 3.9, I think, or 3.10, where it talks about the normal line. But that's it right there. So what we do is if you think of the Earth, then you think of that as as gravity pushing down, and now you have an equation to get to gravity through the tangent line. And so we know this relationship from algebra, right? This is m. Then this guy's going to be -1 over m, right? It's the reciprocal negation relationship. And so then you set a whole new field in 3-dimensional space now that you got that. And in mathematics, we're mostly interested in forces, right? With vectors, there's forces, and then you have force of gravity, force of exertion of one object to another object, how much friction there is. And then you have this whole concept of if you're pushing something over a hill, right? At that point, stickman, right? There's friction that you're having here, but as it goes further and further, there's less and less friction as you go. And so I think for the most part, I think in your physics class, right? You guys have been doing it, and you guys talk to me if I'm not true here. We've been doing mostly things on flat surfaces, right? You put it you know how much effort it's going to take you or how much work it takes you to go from here to here, and it's a flat surface. And that's because that surface friction is being constant. But once you start curving, right, now you have to take into gravity, and gravity is changing every single centimeter
Oh,
as
and
you come
that's what
across.
the differential is for, because then you can find the slope which corresponds to the friction and the gravity.
Well, cool. Is that good?
I get it.
And
Okay.
it is super
Alright.
fun. I mean, it unlocks a whole new world.
Well, that's cool.
I mean, I do recall thinking recently, I was like, I mean, I know like calculus is so useful. It's kind of late. This was like, I was like, what? Why would you want to like find the, like, that's cool that I can find like the slope of a point on a curve, but like real life, what would you use that for? But like that totally makes sense that friction is constant. That's really cool.
Now I totally want to be like an algebra teacher, and people be like, "How is this useful?" And then you just be like, "So, in the next couple of years, you're going to learn this, which goes into this, which goes into this, which goes into that, which allows you to know that how to find the slope of a point on a curve." And they
Right,
just look
yeah.
at you like, "Huh?"
Like you see
Like,
the
and that's how
stuff
it's
you're
useful.
doing with numbers, you're gonna just like disregard the numbers entirely,
Right. And when you
and
do
you're
this in
gonna
algebra,
only variables.
right, in algebra 1, when you're learning this, you're like, okay, where am I ever going to use that, right?
Yeah.
But then, yeah, it's just a whole new world, though.
It's
Well,
just a stepping stone.
I think I now have a second idea for my calculus presentation, which is
Awesome.
topology. I feel like that might be too big of a rabbit hole to go down, though.
I mean, I'm down. That sounds fun. I mean, I'm still
Topology
going down
in
the same rabbit hole of
calculus,
sine
right?
or waves and stuff.
That's
Because
cool.
actually, if I revisit my project, I wonder if I'd understand it now.
You probably would, yeah.
Because there were
Probably
some
would
equations in
understand it
there I
better.
just copied and pasted because I had no idea what it was. Let's see,
I think you would, yeah.
trigonometry,
Go for it. Take a look
Or
at it.
resonant
Or
frequency.
maybe you need to learn the integrals.
Yeah, I don't think he did. Did you do integrals in your presentation? I already forgot here.
I don't think so. I did Fn is equal to V over gamma n is equal to NV over 2L,
Yeah.
which
Yeah.
was for resonant frequency.
I'm going to go one more here on this guy. So what we just did over here is we just did a two-layer chain rule. We good? The two layers were, right, this function, the power function of 2, right? And then the next function was the 3x plus 1, right? Those two functions. So let's jump to, sorry, Christopher, you can look at the trig presentation here. I just want to set this up.
No. I don't think it's I don't think it's calculus. Now, if I wanted to do trigonometry in space, or if I wanted to do like space stuff, now I could probably go in and be like,
okay. I thought you had derivatives in yours. I know there was one person. I thought it was you that had derivatives. I'm pretty sure it was you.
It might have. I might have removed it because I remember removing a couple slides because they were just too complicated.
Okay.
Who knows? I might add those back because that's what I'm intended to do.
Okay, guys, real quick here. Let's go for it. This is a 3-function chain rule. So you should sort of see 3 functions inside here. And it's almost easier to sort of see it this way. So cosine is here, 7x squared plus 1. And this whole thing is taken to the 4th power. Ooh. So there's the original function. I'm going to call it h of x just to give it another name. So what we want is we want the derivative of h of x. And again, it's a chain rule. So let's start from the outside function and move in. So that 4 goes in front as a multiplier now. And then we can still put this, remember, because this one is going to go down by 1 only, right? So 4 goes down to 3.
Yep.
The derivative of the next inside function, which is the cosine. So they'll be multiplied by sine. Sine or negative sine? What do you guys say?
Isn't it negative sign?
Negative sign, okay. And at this point, you could put brackets, you could put a dot, whatever you like.
Okay.
All right, so negative sign. Don't let me forget that little negative there. And then from there, then we're going to take the derivative of the inside here. So 7x squared plus 1 makes 14x. There it is. It's all now on the outside. And now we got to put it together here. So 4 and 14. I think 46, 56.
56.
Yep. Negative 56x. And whichever one you want to put first, that's fine. Normally we put sine first. And then cosine, if you want to put it back into regular form, there's cosine cubed on the back end. Whew, that is cool, guys. There's your chain rule.
Well, that's cool.
Okay. That makes sense.
And then we do like a historical throwback real quickly here, and just because it's used later on. So we have Leibniz, the guy that started our notation for calculus. We moved beyond him, but he did some pretty cool notation. So we do have to look at Leibniz notation. And you guys tell me, oh no, because you guys don't have calculus physics here. Leibniz notation still heavily used in physics, just because it allows us to separate variables anytime we like. And so let me just do it because you guys have some homework questions that deal with it here. And so first things first is we have a function called y is equal to, let's go x. Let's do a little quotient rule here. I should put Leibniz. Let me put Leibniz notation on the side. We good? Leibniz notation just says this. If you want to find the derivative of y with respect to x, and you have to go through a series of different variables, you can separate them out by taking dy with respect to u, and then just multiply that out with du times dx. And so that du is as a middle variable that we're going to introduce.
Okay.
We're doing the same thing. Don't think it's something different. It's the same thing as a chain rule. Okay, it's just we're partitioning the two variables out so we can take them one at a time. So what we're going to do is we're going to do this. We're going to say, okay, we're going to make a u substitution just like we used to do in when did we do u substitution? Yeah. I don't know.
No idea.
Statistics?
I don't...
The only time we used u.
I guess we did not u substitution, but just
and
substitution.
I was the one who used derivatives.
Okay, yeah. I know you did derivatives, yeah.
That was what L was. I was like, what's XL? It's just a different way of doing the like tick, I think.
Okay, let's define u.
Cool.
Since we defined. Yeah, go ahead.
I just get to add on to my resonant frequency. Because I always like to do the complicated things that I don't quite understand yet, don't I?
That's a cool thing to do it. That's a cool way to do stuff. That's the way you learn. Are you also a tactile learner? Do you just like jump into something and just try to figure it out afterwards?
Maybe.
Enrique seems to be the kind that says, I'm going to think about it first.
I'm going to read
now
the
I got a game
instructions,
plan.
actually.
Now I go.
I'm the type of person that does the homework problem before they read the question entirely and then realize, oh, wait, I did it wrong.
Oh, yes.
That wasn't the question.
Oh, boy. Okay,
we balance each other out.
Mm-hmm.
More him than me, but
so let's go for so u is that stuff inside. That means y has now become u to the fifth. And so we technically have two equations that are happening. I should have wrote it like this here. That'd probably be better. Notice we've just separated those out completely from each other. And so what we're going to do is we're going to take dy du. That's going to be 5u to the fourth. I would just leave that alone for now. But what we've just done is we've just done this portion right here.
Okay.
Now let's do this one right here now. So this is going to be du with respect to x now. This one's a little more work. Let's see, this is the derivative. If you need to, chain rule says derivative of the top one times the bottom minus derivative of the bottom times the top over bottom squared. Good there? Or the first times derivative of the first times the second minus the derivative of the second times the first over second squared. Okay, so in this case, the derivative of x would just be a 1. So this would be f of x right here. This would be g of x. So we multiply the g of x without any changes, minus, take the derivative of g of x, which is 3, times the top over the bottom squared. Okay, a little bit of work. Don't get lost in the details here. Just want to just be able to simplify just that big piece there. So multiplying by 1 doesn't change anything. Okay, are we good there?
Yeah.
Okay, so now what we're going to do is we're going to put everything back together again here. So we've separated them out. So now I just need to multiply this one and this one back together again. And so initially when we multiply that out, it's just a 5u to the fourth still. And then we multiply times what was left on top and the bottom. And then we back substitute what the u actually means. So it's 5 original function as it was before, multiplied by and there it is.
One new message.
Thank you. Okay, are we good there? So still chain rule, still the way it was before, but it lends itself to allow us to separate variables.
Right.
So that you would get the same thing if you did the chain rule and
Absolutely.
Okay.
Should we do the chain rule?
I get it.
Yeah, and
Yeah.
I want to say maybe like customarily, I guess maybe in calculus, you see something like this. You know, you see something that I'm going to just write. You don't have to write it with me here. I see something like that. I'm thinking to myself, whoa, hold on. I'm going to take this power rule. That's easy enough, right? That goes in front. But then I have to deal with the whole chain quotient rule inside here. It's almost like that. So instead of dealing with all at once, I can say, okay, off to the side, forget this. Off to the side, I'm going to take the derivative of just, you know, the quotient rule, because that's going to take a long time. Right? That's kind of what it means.
Okay.
And so now with the physics applications, it means that you can take a derivative of the gravity by itself. You could take derivative of another force by itself and then combine them together later on. That's kind of what's in there. Okay, so chain rule, I think we got that one covered.
Yeah.
All right, anything on 3.7, inverse functions? Or you guys are not there yet? And if not there, that's fine. That's what we have Wednesday for.
I have finished the 3.7 lectures and they mostly make sense. I think once I'll tackle the homework tomorrow, well, today and tomorrow, and see if I still understand it.
Okay.
Yeah, I haven't done 3.7.
Okay. Let's see. The only thing Wednesday, I will be in meetings all day here. If we, the only thing I can do it is probably after 5 or so. Is that okay with you guys?
On Wednesday?
Yeah. If we're gonna
Okay.
get together.
That works.
Yeah, okay.
Unfortunately, it does work. Sometimes I have stuff later on Wednesdays, but I don't this week, so that is
Okay.
good.
Oh, perfect. Okay, I'm glad it worked out. Yeah, so let's do that. You guys finish up whatever you can. I will send you guys the video of what we did in class today, which was maybe like, I think it was 119 was one of the homework questions, 131, 151D. So in the hundreds.
Okay.
All right.
We'll get those done.
All right. Sounds good. Thank you for taking the time to meet with us separately and
Oh,
work through
absolutely.
it.
Thank you so much.
Yeah, absolutely.
This helped.
Good. I am glad. And if you still need, even after, I really want to say, because I teach you guys, right? I don't teach calculus, I teach you guys. So if you need extra help, please ask. If you just feel that you're not confident for the exam yet, still on Thursday, and you want to get together on Thursday, that's fine too. Good. I would want you guys to be done with the exam before Monday, though, right?
Yeah, I also would like to be done with the exam before Monday.
That would be nice. I would
Yeah.
would like that.
Okay, sounds good.
I don't want to have my bucket next to my seat on the table is in one sitting with the bucket or any.
That's
I remember you saying the first take home in one sitting, and I was like, so I've got a bucket and lots of time. Oh, there it is.
For free smiley. I was hoping that would show up today. Thank you. I will save the smiley. Yeah. It's
I wonder how many are left on the actual IRL boards.
I feel like I heard you guys talking about that at the beginning of one recording. I don't remember which one it was though. It is a little hard to hear people. This is the same with physics, but like I'll hear like Sadie's voice saying something. I'm like, it's like I know she's either asking a question or like asking a clarification. It'd be great if I could hear it, but I can't.
Oh yeah, okay.
Usually I can. Usually I can. I mean, I understand what she asked because you'll like write it or something like that, so I can follow.
But
it is. I mean, it is funny. Like you could just listen to a recording, and it's like, so like most of the time it's Sadie, and then occasionally, Kate and Eli will jump in. And like I never hear Taya unless Mr. Hanjiev asks.
I mean, and then like, even hey, Taya, then how you can't really hear Taya.
Well, I can hear her voice, but I have no idea what she's saying. But...
What I'll do is I'll restate the question. I know I've done it in the past, and then I just forgot about doing it here, but I'll do that.
Yeah,
I think much more clarity.
I definitely
when the question is restated.
Sympathize with you guys having to remember to do that for the online students, because even like Miss Shotwell did it for one of her lectures, and then like after that, she like stopped doing it.
Yeah, because you're the flow of things, right? If a question asks of you, then you just go and answer. But yeah,
exactly.
Got to remember it's for the video. So
yeah.
Okay. Well, wish you well, and let's meet together on Wednesday. I'm going to have a pretty busy Wednesday, so just email me, remind me.
Okay.
I'll put it on my calendar right now, just so I don't forget, and hopefully we can get together. And what's better for you guys, later on, or because I'm thinking the earliest probably be about 5:30 for me. Is it better to do it like that, or a little bit later on? Let's maybe decide a time right now. That'd be better.
Well, so I have dinner around like 6:15. What about you, Enrique? When's your usual dinner time?
My family's been trying to have dinner earlier, so it depends. Sometimes it's like at 5 or 5:30, and sometimes it's at like 6:30.
Okay.
I mean, I would probably be fine to just eat in here or have dinner after. So I don't think that'd be a huge deal for me, especially if it's like for calculus. Parents would probably say, yeah, go to your room. Don't eat dinner with us.
Okay, and if you want to email me maybe Thursday morning, email me questions ahead of time. Then I'll have sort of a list starting to go. And I'll post the videos from today's class and actually from the homework class that we did on that extra Friday. So you will see like extra homework day.
Cool.
Okay.
There'll be 2 videos posted and then today's video. Yeah,
And
sorry.
then you said something at the beginning about finding out a schedule for the presentations. Do we have to sign up for spots now?
Yes, we do, but at least let's do that here. Thank you so much.
So I remember you saying that and pulling up the schedule.
Mhm.